Alright, welcome to the fourth solution video for the BC PC Programming Contest 2017. Really quickly, before we start, I just realized I forgot to show that our last answer worked. So we'll do that real quick. So there's the input. No yes is the expected output, and that's right. So this doesn't necessarily mean it works, but it does mean that it works for the example input given, which I wanted to show, but I forgot. So that's the example input. If you want to try that yourself. All right, so on to problem 4. This is the obligatory arbitrary number problem. And this year's properties was whether or not a number is prime. Interestingly, 1 is the only natural number, the only number that's greater than 0, the only positive number that's neither prime nor composite. All other numbers are either prime or composite. So for this problem, you had to figure out whether or not a number was prime. And this problem was interesting in the fact that you couldn't just do the obvious, straightforward solution. You had to think a bit more creatively in order to get something that was feasible to run within the 5-second time limit. One thing to notice is even if you managed to get a solution where 10 to the 9th plus 7 could finish in 5 seconds, there are up to 100 numbers to input. So you can bet that one of the test cases has a whole lot of numbers that are very, very large, very close to this integer.max value limit. This is slightly under integer.max value, which is good. Integer.max value is about 2.14 times 10 to the 9th. So this is under there. So we can still use integers. You can use longs if you'd like, but we can still use integers. But we should keep in mind that you do have to have something where this should run in well under 1/10 of a second, or well under a second at least. It shouldn't be getting close to 5 seconds because then you're going to have issues. So for this class, we are going to need, or for this problem, we'll need a new class with public static void main, and then obviously we'll need a scanner as usual. And then we'll need the number of test cases, and then we'll need a for loop. Alright, so I'm going to make, well, I'll do that later actually. So int to check equals s.next int, so we're given the number we're supposed to check. And then there are 3 cases basically. Either it's prime, it's not, or it's 1. So we're going to go with the case that it's 1 first. So if it's 1, then we have a special case. And then if it's not 1, we want to know whether it's prime. So if it's prime, then we want to check it, and if it's not prime, we don't really care. So if it's 1, we'll just sys out neither. It's neither prime nor composite, as the problem describes. And if it's prime, we're going to print prime, and then if it's not prime, it's composite. Okay, so that's cool. So all we have left is the isPrime method, helper method that we said we wanted. Almost. All right, there we go. So then it's check. So that's the number we're going to check. So there are 2 ways to do it. The straightforward way, the way that you would pretty quickly think, is you want to check all of the numbers bigger than 1, because every number is divisible by 1, so we don't really care about that. You want to check all the numbers bigger than 1 and smaller than that number and see if any of those numbers are factors. And if any of them are, then you know it's not prime, because it has, well, it has at least 3 factors. It has 1 itself and then a third number. So if that's the case, then it's not prime, so we can return false. So let's implement that really quick just so we see what it looks like. So we go through all the numbers, and we want to see if to check mod I 0, and if it is, we return false. If it isn't for any of these numbers, we want to return true. So that's kind of the idea. The issue with this is, let's say we have 1 test case and we have 1, 2, 3, 4, 5, 6, 7, 8. There you go. So 10 to the 7 takes quite a while to run, and if we had to do this 100 times, we wouldn't finish it within 5 seconds. This here took, I don't know, maybe 10, 15 seconds. So the idea with this is right here we're checking 10 to the 9th numbers, and a computer really can only do about 10 to the 8th operations per second. Usually you want to stay around 10 to the 7th, but sometimes 10 to the 8th if you want to cut it close. But it can't really do 10 to the 9th, and it certainly can't do 10 to the 11th, which would be this case. So this unfortunately is too slow. So the trick we have to realize is that if, let's say, some number C is prime, let's say it's not prime, let's say it's composite. If it's composite, then it has to be some A times B, right? And that's all we really have to find. We really only have to find whether or not there's one pair of these two numbers. We don't care how many factors it is, like the problem says. We just care whether or not it's prime. And to do that, we just have to see whether or not any factors exist between 0 and 1. So really, we only have to find one of these two numbers, because we know if one exists, the other also exists. It could be the same. A could equal B, like if C is 9, then A and B could both equal 3. But we just have to find whether one of them exists. And if A times B does equal C, then we know the minimum of A and B is, the highest it could be, highest the minimum of the two could be, is the square root of C. Otherwise, then, right, they wouldn't equal C. If they're both bigger than the square root of C, then A times B would be bigger than the square root of C. So really, we only have to check math.sqrt of toCheck. And you can do less than or equal to for that, but just to protect against possible issues, I'm going to add 1 to it, and then guess to an int. And then I'm also going to do math.min of this and check. So what that does is I never want to check. I never want toCheck to be the number to check. For example, if toCheck was 2, the square root of 2 plus 1 is actually bigger than 2. So that would be an issue, and we wouldn't want to check 2. So casting it to an int might or would help that. The reason I add 1 instead of going less than or equal to is because sometimes doubles aren't completely reliable with them being exactly on. So for numbers that are square numbers, you have to be careful because there's a chance that when you do the square root, it'll come like 4.99999 could be the square root of 25 instead of 5.0, and then you could run into problems. So it's probably not necessary, especially since we didn't have that many test cases. But that's one way to do it. And doing that, you'll notice that that took so much longer to run before. If we do it now, it gets the answer right away because it only checks 10 to the 5th numbers approximately, which is much faster. So this solution is fast enough to work. It gives the right answer. We can try it with the example input that we're given. So four test cases. 9 is composite, 1 is neither prime nor composite. In 2017, the current year, as well as 10 to the 9th plus 7 are both prime. So that was the problem 1. More teams than we expected actually figured this out. We thought this would be a pretty confusing math trick that not a lot of teams would get, but teams did very well on this. I was very proud of how many teams were able to figure this out. But this is where things got much more difficult. So this really is impressive to be able to get a problem of this difficulty in the short amount of time you had to compete in this competition. So congratulations to everyone who got it, and thank you for competing. We'll show you the future much harder problems if you'd like to keep watching. Otherwise, you can see the problem analyses if you don't want to spend your time going through this entire video. So thank you.